All right. So we have one more set of derivative rules. After this, we'll be done with derivative rules, and then we can start putting together our quiz review, which we can start a little bit today, but we can work on it Monday and Tuesday in preparation for our quiz next week. Okay, so here are a couple of things to recall about logs and exponential functions. Logs and exponential functions are inverses of each other, so they're going to have some relationships that allows us to cancel some things out. So one thing is natural log of 1 is equal to 0. Natural log of 0 is undefined. E to the 0, anything raised to the 0 power is 1. E and natural log, they're inverses of each other. So if I stick one into the other, or e to the x into natural log, or natural log into e to the x, they're going to find a way to cancel each other out. So e to the natural log of a is simply just a, because e and natural log have a canceling out property. And natural log of e to the a, we can use log properties here. That a can come down in front because we're talking about a natural log property, and then natural log of e is just 1, so it's just going to be a that's left over.
Natural log and
you put in in terms of natural log and e, they are inverses of each other. But let me see if I can build that relationship for you. Give me a second. Let me see here. Okay, so here's the relationship here. Let's say y is equal to natural log of x. Natural log of x is the same thing as log base e of x. Easier to see that relationship there when we see that base. And if I do e to the y equals x, these are equivalent to each other. It's just that this is in natural log form and this is in exponential form. So they are inverses of each other, meaning that if I have y equals natural log of x, and if I want to create this equation, I can flip the x and y around. So x equals natural log of y. And if I solve for y here, x equals log base e of y, y is equal to e to the x. So if I find the inverse of natural log, I'm going to end up with exponential function. Yeah. All right, so derivative of exponential functions. Let's review something that we already know. E is basically itself, but if we have something that is other than the x, we got to do a little bit of chain rule. So the rule that's probably better to remember for involving exponential function base e is e to the u times u prime. We still involve the original function as part of the derivative, but it's if it's anything other than the x, we got to worry about that exponent's derivative. So e to the u times u prime. Now a are bases other than e. So a can be base 2, base 3, base 10, base 20. Now the derivative rule is similar to e to the u times u prime, but there's a conversion that has to happen into base e. So the derivative is natural log of a times a to the u times u prime. So it's a little bit, we still have that original function showing up. We still have u prime showing up, there's just needs to be a little conversion into base e as part of the derivative rule. So natural log of a times a to the u times u prime. So let's do an example here. If our function is 2 to the x plus 3e to the x, you have one that is base 2, which is a to the u, and one that's base e, which we can use e to the u. So let's find f prime. F prime equals, so we want to use this rule here. So what comes first?
Natural log of 2.
Yeah, natural log of 2. That's just the coefficient. Okay, so it's just some number, it's not a variable. Times 2 to the x times 1. Okay, so I want to kind of just show you that technically you don't have to put a 1 there, but I want to show you that you always want to look for that u prime as part of your derivative rule. Okay, so that's the first part, plus 3e to the x. So we keep the 3, coefficient stays. E to the u is e to the u times u prime. Okay. So these are kind of related. I just like to think of this as the parent of derivative for exponential functions, and this is the expanded one involving other bases. Okay, same with derivative of natural or log functions. If I have base e, I want to use natural log of u. If it's base 2, base 3, base 5, any other logs of other bases, I want to use this log base a of u derivative rule. So base e, the derivative is just nice and clean, just u prime over u. Before we said 1 over x, but u prime over u, we can use that for all the natural log derivatives, taking into account the u prime, which is a lot of times more than just a 1. Now, log base a of u is still log, all right? We're still going to get this to show up, but there's a little bit of conversion that has happened. So it's going to be, there's still u prime over u, but in front, it's going to be 1 over natural log of a. So it's 1 over natural log of a times u prime over u. There's a coefficient that's sitting. So it's basically the same rule with a little added extra conversion and coefficient there. All right, so example 4 here. Find f prime if function is log base 4 of x minus 4 natural log of x. Let's find our derivative here. This is log base 4. I'm going to use this log base a rule. So what comes first?
Log of 4.
Yeah, 1 over natural log of 4. It's just some coefficient times what? Good. My u value is x, so u prime, the derivative of x simply 1, so 1 over x minus 4 is a coefficient, that's not going to go anywhere. We do u prime over u for natural log, so also what? 1 over x. There's no need to worry about common denominators. You can do this any way you want, but if you wanted to, you could. No, we can't. It's hard to clean up. We just leave it as 2 separate fractions there. Okay, any questions? So that's it. We've covered all the derivative rules, but I think I put in your packet a sheet where you can practice all your derivative rules. Now, I do want to talk about something that helps me remember the difference between these two rules. I know that a to the u and log base a, they all involve natural log of a, but sometimes I want to make sure I remember, right, is natural log of a in the numerator or is it going to be in the denominator? And what helps me remember it is if you see how my exponential function e to the u has no denominator. So I know that my a to the u times u prime, there's no denominator here. And that helps me remember the natural log of a goes in the numerator. But with logs, there's always a denominator portion, u prime over u, log base a of u is also u prime over u. So that helps me remember that, okay, there's a natural log of a component, but that's going to go in the denominator because there is a denominator that shows up as part of my derivative. So that helps me remember between where that natural log of a goes, either in the numerator for the exponential or denominator for logs. Okay, you guys want to try 1 through 3? See if you can go through those derivative rules. Okay, check your answers. Any questions? Okay, next page, log differentiation. Pretty good. All right. Let me review some log properties. So we know natural log of 1 is 0, natural log of e is 1, and then this is the product property, quotient property, and the power property. So product property says if I have natural log of a times b, I can expand it into natural log of a plus natural log of b. The nice thing about that is we can take potentially a messy problem and split it up into individual smaller portions and work on them individually. Same thing, natural log of a over b, I can expand into natural log of a minus natural log of b. And then this power property allows me to move the exponent in front without changing the overall value. And sometimes that helps us see things in a that allows to work on the expression a little bit easier. Okay, so what is log differentiation? Log differentiation is simplifying a non-log function using log properties to expand before differentiating. So there's two uses for log differentiation. One is where you're trying to find a derivative for a function that otherwise would be a messy combination of chain, quotient, or product. And if we force this into a log expression, we can take advantage of all these properties and split them up into individual parts and then find the derivative of them individually. Now, the derivative will look a lot messier, but it's okay because you can just represent that as one of your answers, as a version of your answer. There's no need to clean up. So just know that if you go through log differentiation, your answer will be a little messier, but it's fine because you've reached a version of the answer. The second example is where we have no option for a derivative rule. So this is a rule that doesn't exist. This is a variable raised to a variable, right? X raised to something that's a variable. We have a variable raised to a constant, which is power rule, we have a constant raised to a variable, which is an exponential rule, but we don't have a rule for a variable raised to a variable. So the strategy there is, if we can force this into a log expression, that exponent can come down, and then we can have more availabilities in terms of options for us when things are not stuck in the exponent region. Okay, so let's do the first example, and I'll show you the second example. So this is more of a good thing to know, but in terms of what shows up on the AP exam, if there's a log differentiation problem, it's usually going to be something like this, where you have to use log differentiation to get to your answer. Okay, so let's go through the steps here. Find the derivative for y equals x minus 2 squared over square root of x squared plus 1. Now, we only can do log differentiation if there are no logs to begin with. Okay, if there's already a log in the expression, we don't want to add another layer of logs. That just makes the problem even more complicated. But we're going to introduce logs into the problem. I'm going to clean up that radical as I go along. Okay, so no calculus yet. We're just forcing logs into the problem because we want to use properties to split this up into easier parts. Okay, so which property can I use on the right side here? Yeah, that's right, the quotient property. Yeah. Okay, so we're just going to do natural log of a over b becomes natural log of a minus natural log of b. What else do you think we can do to make it?
Exponent.
Yeah, the exponent can also come down. Now, we don't have to move the exponent, but if we don't move the exponent, the rule for derivative, natural log of u, is going to be messier because you got to deal with chain rule within the chain rule. So it just makes it a lot cleaner if that exponent can come down. Now, there's no calculus here. This is not part of any derivative rule. This is simply an exponent power property, where we can bring that 2 down. We're not changing the overall value of anything. We're just making it easier for what we want to do, which is find the derivative. So up to this point, we haven't done any calculus. We just rearranged it in a way that will be easier for our calculus step. So any questions here? Okay, so now we want to go into our derivative rule. The right side is simply u prime over u. That should be pretty clean. Now on the left side, the y is no longer by itself, so guess what we have to do a little bit of? Anytime y is not by itself, we got to do a little bit of implicit. So there's going to be a little bit of implicit that shows up on the left side. So the rule for natural log of y, u prime over u. So 1, the derivative of y is 1, so 1 over y. And then we always attach dy dx whenever we're involving y's derivative, right? So 1 over y dy dx. And then next up, we just apply natural log's rule. Natural log is u prime over u. 2 is a coefficient. It's just going to hang out in front. Natural log of x minus 2 becomes 1 over x minus 2. Minus the 1/2 is a coefficient for the second expression, so that stays. U prime over u, x squared plus 1 becomes 2x over x squared plus 1. Okay. So that ends the calculus step. The rest is cleanup. Okay. Any questions so far? Okay, so our goal is to get that dy dx by itself. So I'm going to multiply the y over to the right side. And I'm just cleaning up my fractional values as best as I can. Now, this is a function to begin with, so we shouldn't have to have a y variable in our derivative. So what do you think I can replace y with? The original equation. Yeah. So your derivative will look messy, but I mean, it's a derivative, and you're never going to be asked to find a common denominator. You can just leave your answer in that unsimplified form. But it's a good tool to know, especially if, let's say, you don't want to have to go through a messy combination of chain and quotient rule in this instance. It's a lot faster to get to the derivative. Okay, any questions there? Okay, let's look at the next one here. Okay, so it says find the derivative of y equals x to the 2x plus 3. We have to recognize that there's no rule that can handle this, right? There's no rule that can handle a variable raised to a variable. So that's the first thing for us to recognize, that we don't want to force a power rule or an exponential rule into this instance because it doesn't fit that category. So we recognize there's no rule that can handle this, but we can use natural logs to force that 2x plus 3 to live elsewhere. So first thing, we're going to take the natural log of both sides. Okay, so now that we're in a natural log expression, what can I do with that 2x plus 3? Put it in the front. Now, when you put it in the front, make sure you keep it protected with a set of parentheses. And I want to show you there's something else we got to worry about here. So once that 2x plus 3 comes down in front, put this on a separate page here. Okay. We do have a rule available to us. No longer do we have exponents to worry about. Left side is still going to be implicit, like how we saw, but the right side, we got to do what? We got to involve what's to find the derivative here. Product rule. Okay. So that's the thing that's always going to happen with these problems. We're gonna have to, there's no way around product rule. We got to go through product rule. But at least we have the ability to find the derivative before we didn't even have a rule to begin with. So we're able to find something that actually works. Okay, so go through product rule, f prime g plus f g prime. And the left side is just 1 over y dy dx. Okay, again, your derivative will look a little messy, but it's okay as long as you get dy dx by itself. So the y moves over to the right side, but because we started with a function, we should be able to represent our derivative purely in terms of x. We can replace the y back with our original equation as well. Okay, any questions? I just thought this would be a good problem for us to try together. This is a older FRQ problem. But it showed up on the AB and BC exam. Let me kind of talk about this here. It says consider the curve given by x squared, xy squared minus x cubed y equals 6. It says find the derivative. So just looking at this equation here, what's needed if we want to find the derivative? Implicit and product. How many times for product? Once. Okay. So don't look at, part A, they're telling you what the answer is. So you're not going to start with this. You're going to start with this equation, find the derivative and see if you can get it to look like this. So that's your goal. Your part A is just, can you get from this to this using what you mentioned, implicit and product. Okay. Part B, find all the points on the curve whose x coordinate is 1, then write an equation for the tangent line at each of these points. So you're going to use your slope, use your order pair, see how far you can get. And then part C, find the x coordinate of each point where the tangent line is vertical. Let me point this out here. Tangent line vertical, what does that mean? That's good. That's non-negative with root of. So even if you, this problem is nice because even if you messed up for part A, you can still rely on A to help you with B and C because they can build it off of what's already there. So it's a little bit messier in terms of what's going to happen here, but see how far you can get. The keys on the back, but I'll go through each part. Okay, so spend a few minutes and I'll be right back.
That's what it is. Yes. Try this. Yeah, so sometimes it's very important. What, of course, it is like this very essential. That's like, it's 1, 2, yeah, that's like, I don't want to say one. So then I needed to keep one back into the new song and I just said, one brother. I got y squared minus y equals 6. So, yeah, so y equals 0, y equals 4.
No,
If you factor it out.
you can look at it in the back, it's real negative two.
Oh, it's not bad.
That's in the back. Oh, it just knows it.
Oh, yeah, I did subtract 6. It's at 8 with a 0. It's that particle one is still last like this work. No.
Yeah, I did the same thing. You put this to the other side.
Plug into the read. Minus one. Yeah, y equals 3, y equals 3. That's what I got. I got y equals 3, y equals 3. I saw what I did.
Yeah.
Wait, when did you do that?
Because that's from.
I got it, just derivative. Oh, okay. And use the slope and the coordinates to do the equation.
I do remember that one, exactly.
See, 1 for 1. I can see 1 for 1 is good. Everything person is sitting. It's
Plug into the into the.
it's like it's the excellent one. It's to put them down. Thank you. Once unlock them, give you that. It's real, but it's that's the place for. Let's leave. I thought it answered, but I can't do it. I still do it. What? like so. Well, what he did probably.
Done steep
Yeah, but I.
and not from the beginning.
What he said, but he basically said it not. It's found, just. I would drive you to far, the original.
Oh, people.
Because you got like live with 1/2 X. Oh, right, one of these falcons. When I said there was denominator. And then the original.
Okay, you don't stop this that.
You got one thing, look, it's very see what you get to say. I just don't think. Yeah, the chocolate. Absolutely. The slow goes in. It's very. That's all. It's just like those are all the live different. So it's just apply. It's not a live. But now you have it. All the parts of the line is.
Yeah.
And then it goes. One half of that square. But she got some stuff, you something that line. But I did the same thing. But I had to go away. I did keep there two X, simplifying. But I just did the substitution the other way. I substituted in a loss. But I don't know, and I still got the same, I managed back. And I'm keeping it right. So the numbers were something. So this is here. It's just been really. No, because that's. Yeah, I'm getting some weird. Something that makes, but this is the answer. Wait, I just got a 0. No, C. That's the answer. I got X. I was thinking that bad. I saw it's glitching out like so. Bro, I got a 0. That's the next year. Oh. And you.
Yeah.
One single you can find the bags. I know he's doing all I do, the whole thing. I used it the whole thing, or which one's so. Only the type.
Okay, are we good with part A?
Oh, it's all. The horizontal don't seem very. Yes.
Okay, so part B, find all the points where the x coordinate is 1. So this involves the original equation. So we go through the original equation. So because this equation has x and y's in it, it's very possible that you have 2 ordered pairs with x values of 1, right? It doesn't have to pass a vertical line test, so it's very possible they get more than 1. Okay, so we have 2 ordered pairs. 2 ordered pairs where x is 1. Write the tangent line equation at each of these points. These points may have different slopes. We'll have to insert them into the derivative separately, find the appropriate slopes for each of the points, and then build our tangent line equation. Okay, so that's part B. Oh, time's running out. So I'll finish this up on Monday. I will have, yeah, you guys have the homework over the weekend and we'll start our test review on Monday. Okay, come get your phones. Yeah.
There's a big part. This one says that might be what I got. It's also just. I don't read that very carefully.
What?
It's also.
Sorry.
It's Friday. Actually, I have a bunch, but I'm not going to. Yeah. That's every single dumbass is. Like what? If I put this. I got this. It's just still